Okay, so we are pivoting here a little bit. So in the last class, we saw the cellular structure. So looking into the cell membrane and the cytoplasm and all those kinds of things. But in the interest of time for this class, what I'll do is I'll try to record the rest of the class, the rest of chapter 5. But in here, let's start talking about the energy for life and how that plays into this equation. So, out of the three most critical requirements for life, energy is one of them. So, the elements, the CHNOPS elements, that is one. The second is water, where all the reaction happens. And the third is the energy requirement. Now, the energy is required by life to do primarily two things. First, so what could be the primary? Why do you need the energy? So why do you need food? Like that's the thing. Like this is energy is food. So why do you need food? To do what? To do what? To move. Okay.
For everything.
For sustenance, right? Yeah. So that's what. So to sustain life, to move, to reproduce, to protect itself. So for everything, it needs energy. Now, energy is also required for the growth of life, right? So like you need energy for the growth. You need energy just for its maintenance, to do day-to-day activities. There is this big idea about energy requirements for the origin of life, how that came in. But for now, let's keeping it simple. We'll like try to think about. So you already have life, and how for the growth, maintenance, reproduction, those kinds of things. What kind of energy is required? What that energy is? How does it get that energy, and all those kinds of things. Okay. Now, in physics or in chemistry, we have a field called thermodynamics that deals with energy or the transfer of energy from one place to the other. We have a field called thermodynamics, so we know that. In thermodynamics, there are like different laws, and we saw those laws a little bit in geochem. Right, so I'm not getting into thermodynamics, but just a little bit. So thermodynamics specifically deals with heat energy, okay? And dynamics is the transfer or the movement or the transport or transfer of that energy. Now, in thermodynamics, we briefly saw that heat is a form of energy. How would you define heat energy? What is heat energy? We have an intuition of light energy, heat energy, sound energy, nuclear energy. These are all energies. But when it comes to heat, what is your intuition? How would you define that heat energy? That is another energy. But what is internal energy? So is internal energy the same as heat energy? or is it there is some difference? There is also a term called work, right? So what is this internal energy related to? How can you define this internal energy?
The vibrational energy between molecules and
Between molecules or of the molecule?
of the
Right. So this is related to the vibrational energy and vibrational kinetic energy, to be more specific. So what physical parameter is this is this internal energy, which is the kinetic energy, related to? What physical parameter that we usually think about quite readily? Yeah, so this is the temperature. This is related to the temperature. So you increase the temperature, you increase the internal kinetic energy or internal energy, right? Then there comes work. I am not going into that because now is not the time. So this is P del V, right? And then there is this heat thing. So what is this heat energy? How is this related to this entire business? So I understood kinetic energy, I understood work, but what is heat?
Energy in transit,
Because of?
temperature difference.
Exactly. So this is the energy that is coming, so in transit. So this is in transit because of a temperature difference. So when one body if the energy of one body is going into the other body, because there is a temperature difference between them, then we call that energy as heat energy. That's heat energy. A body in itself will not have heat energy. A body in itself will have what energy? Internal energy. Because of the temperature. So it is also related to the temperature. So body in itself, upon increase or decrease of temperature, will increase or decrease its internal energy. But when that energy is transferring from body A to body B, because of a temperature difference, that energy in transit is called heat energy. So body will not have heat. A body has internal energy. A body can give off heat. Right? Okay. In this, I'm not talking about the work, but I hope that you guys appreciate this all work business in here. Okay. Now, there are different laws of thermodynamics. What is the first law of thermodynamics? Or so let's talk about the zeroth law of thermodynamics. That is so fundamental that we don't even give it the first law. We call it the zeroth law. It's so fundamental. What is that? If body A and body B are in thermal equilibrium, and body B and body C are in thermal equilibrium, then body A and body C are in thermal equilibrium. I will not elaborate on that. So this is the zeroth law of thermodynamics. This is the same law we use thermometers to get the temperature and all. The first law of thermodynamics is energy conservation law. Okay, the first law is the energy conservation. Can someone tell me the first law of thermodynamics in short as a formula? This is the first law, right? So the amount of internal energy, which is U, that a body will gain or lose will depend upon the heat and the work done, right? So if I give a body 100 joules of heat, that is Q, and the body does 30 joules of work with that, then the internal energy change will be 70. So it's as simple as that. So it's energy conservation. Now if work is 0, then all that heat given will be converted to internal energy, and we call that process, when work is 0, what is that thing called? So this is work, right? I'm saying this is 0. What is that thing called? So what will be 0? The del V will be 0, right? So there is no change of volume in that system. It's called isochoric, right? Now, when the internal energy is 0, what does that mean? Did the temperature change? No. Because if the internal energy is related to the temperature, so that did not change. So when that doesn't happen, it is called isothermal, right? And when the heat is 0, what is that called? Adiabatic. So these are all just names in which so essentially we are simplifying these processes. So whenever we say isothermal, adiabatic, isobaric sometimes and pressure. So in these are special circumstances, and these special circumstances make our jobs easier, because essentially what will happen is something will be 0 or will be constant, some things like that. So these things are there in thermodynamics. So this is the first law in which there is just energy conversion from heat to internal energy to work and all that. The second law of thermodynamics is what? What does that say? The energy of the universe is always increasing. So that's the second law of thermodynamics, okay? So the entropy is always increasing. In thermodynamics, we also, so the second law introduces the concepts of entropy, the concept of entropy is introduced. This is called disorderness, simplistically. So the entropy of the universe is always increasing. So like the entropy of the universe is always increasing. Like combined entropy of the system plus the surrounding, the universe is always increasing. Like that is the second law of thermodynamics. And you will also see, which is very important, is this law, or this this is called the Gibbs free energy, delta G. So this is the Gibbs free energy. This is the enthalpy of the reaction. This is the temperature, and this is the entropy. So using the Gibbs free energy, we are taking two different thermodynamic parameters, enthalpy and entropy, and the pressure is constant here, because enthalpy is energy at constant temperature. Okay, so in this case, we are seeing that the enthalpy and the entropy, using these two things, we can calculate the free energy of the system. Now, why do we call it free energy? So it's Gibbs free energy because Gibbs gave that law. So that's why we call it Gibbs free energy. But there is this free energy. What is free? Why is it called free energy?
Available to do something.
Exactly. So that free energy means that energy is available for you to do some work. So in chemical processes, although a system might have a lot of energy, okay, but that energy is not always freely available. Think of this as, this is the delta H is the total enthalpy of the system, the total energy, right? That's the total energy available for you to, in that system. That's why it's the enthalpy. So we generally call the enthalpy of a reaction, right? Have heard about this term? So delta H of this reaction is minus 232 kilojoules per mole. We call those things the enthalpy of the reaction. But the thing is, that entire enthalpy is not available for you. So that entire energy is not going to come out and serve you. For you, you will get, someone is going to get some cut from that entire energy that is available. For example, when you get a salary, when you get your salaries, who gets a cut? You don't get that entire salary, right? So if you're earning $100, who gets a cut? The taxes. right? So that energy is, so that money is there, it's yours. But you are not getting that full thing to use. So imagine that this is your gross salary and this is a tax. This is the entropic tax. That is inevitable. You have to give that tax. So whatever remains is what you can actually use. So that is a free money. I mean, not free money, that's a free energy, right? So that's the free energy of that reaction. You always think that we can, so what Alan does in his lab is he can calculate the delta H of reactions. Now this delta H is you can calculate the delta H by calculating what is Cp? Heat capacity at constant pressure. So what is heat capacity? The amount of energy exchanged to raise the temperature of a substance by 1 degree Celsius, right? So a reaction will have a Cp, any reaction will have a Cp, and that Cp is going to change with temperature. When you do all that, you try to understand how this Cp changes. You can, this is very simplistically I'm writing, maybe it's not that accurate also, but just think that this delta H can be calculated from lab things by calculating the Cp versus time, and this can be done in calorimeters. You can do these things in the lab. From this you get the delta H, but the interesting thing is not that entire energy is not available for your use. So you can eat food, but not that entire energy is not going to be useful for you. So there will be some wastage, there will be some entropic, there's some tax that involves. So you will have to eat more than this to actually, so like think of it as that, okay? So that is why it is called the free energy. So that is free for your usage, okay? So you can calculate all that. I'm not getting into like the details of this, but anytime this will be key to understanding the reactions, and this is related to the K equilibrium of the reactions. So at equilibrium, this is the formula for the delta G at equilibrium. Also, in electrochemistry, we also have the E naughts is the reduction potentials, right? So at equilibrium, the delta G can be calculated by using electrochemistry. So Shri actually does this in his lab. So he can actually see at what voltage things are starting to happen. And if that thing is maintaining equilibrium, you can take that E naught, say 1.1 volt. Okay, we'll take that 1.1 volt, you will take F, which is Faraday's constant. What is Faraday's constant?
96,500.
What is that thing?
So, 1 mole of electron, charge of 1 mole of electron.
Correct. So that is a charge on 1 mole of electrons. And what is N here? The number of moles. So your E naught, which is the reduction potential, which is what you can actually measure using an instrument called the voltmeter, can take that, can take the number of electrons, so take the number of moles in that process, right? If copper and zinc are exchanging electrons, so the N will be what? Think about it. So it will only, you just have to see how many electrons are getting transferred in that reaction. Okay? And F is constant. This you can measure from that instrument just by plugging in. You can get the delta G, isn't it? So if you get the delta G, you know, if you know the temperature, R is a gas constant, you can know K equilibrium. So from an electrochemical instrument, like in electrochemical measurement, you can actually get delta G if this is in equilibrium. Once you get delta G, you can also get ln K, which is equilibrium. So all these things kind of like you can get together. So delta G, or the free energy, is at the center of all that. And this is the energy that we'll be talking about. This is the energy that is required for our survival, for protection, for growth, for everything. Okay? Now, there are certain differences in which when we eat, you cannot just have, so the first law says energy is getting transferred. Okay? So when you eat, you are converting chemical energy into, so why you are eating? Maybe to move. So you are converting electrical energy into mechanical energy. Sorry, chemical energy into mechanical energy, right? But you have to constantly eat because you are also dissipating. There is energy losses as well when you are. Otherwise, you can just eat once in your life and then just interchange those energies. That doesn't happen because there are energy losses. You can think of those as the taxes or something that is inevitable. You have to constantly earn money to sustain yourself. You cannot just earn money once and then convert into food, and then that food gets into, you cannot do that. So there has to be constant gaining of money. So therefore you'll also have to have constant gain of, you have to feed your system constantly. Okay? So that is there. Now we will see what are the different types of organisms exist, because there will be two parameters on which you can differentiate these eating things. One is the source of carbon. Where is that carbon coming from? Is it coming directly from CO2, or is it coming from an organic compound in which already that CO2 is fixed? Okay. The other is the source of energy. So based on, there will be two factors. The energy and the carbon. So source of both these two. So depending upon the source of energy and the source of carbon, we will now see what are the different types of eating things that the universe can actually do. Okay, this is just the whatever we have been talking about. Just to get a few definitions straight, you will hear about a few things called anabolism, catabolism, and metabolism. Metabolism is just catabolism plus anabolism together. That is called metabolism. Very simplistically, anabolism you can think of as biosynthesis. So when you are taking a carbon based, like say you are creating more complicated carbon based molecules, that is anabolism. So do you do anabolism? Do human beings do anabolism? Do you biosynthesize certain things in your body? No. Generally, typically we don't. But you can imagine that when you're eating food, you're breaking down the food, so you are doing catabolism, right? So you're eating that big complicated carbohydrate, and then you're breaking down that carbohydrate, and then you're assimilating that in your body. So that is called catabolism. Why do you do that? Why do you have to do catabolism?
To release the energy.
Exactly.
from inside.
Exactly. To just release that energy. So when you're breaking down a complex molecule, you're trying to release the energy, because breaking of bonds releases energy. It also requires energy. Now that's the thing. It requires energy, but it also releases energy. Now it depends if the requirement of that energy, if it is less than the final amount of energy produced, then the energy produced in total will be greater, correct? So if you spent 5 kilojoules to break something, and when you broke it, you got 200 kilojoules. So finally you got a lot of that energy out. So that process becomes what? Exothermic or endothermic? Exothermic, because the heat is getting released. Although you will always need a slight amount of activation energy to do things, right? You will need activation energy to do things, but so if this is your reaction coordinate, product, reactants and then going into products, and if this is your energy, this is your reactant, this is your product, this is activation energy. But the final energy of the product is lower, you can see. Right? Correct? I hope this makes sense. The final energy is lower than. In between, you have to take that activation energy. Otherwise, if you don't need this, there is nothing stopping from this to directly come to this. So this will not have stability if you don't have the activation energy. Because if this is at the top of a hill and it can just roll down, there has to be something that is stopping it from rolling down. Otherwise, it will just roll down. Why is it stopping there? Make sense? Because it has to cross this energy barrier hill in order to come to here. That this energy barrier is called the activation energy. So you need to spend some energy to start with. So just like a business can be profitable. You can get more energy out. But even if you're getting more energy out, you have to get a little bit of the initial money to start that business. You cannot just have a great idea and start earning business. You cannot do that. You have to get that money, start that business. So that is the activation energy for that business. Similarly, even if the reaction is exothermic, you need that initial energy to go up that hill. That is why I think you feel lethargic after eating. There could be 10 more reasons, but this could be another reason, right? Because I don't know if that is correct or not, but in order to burn food, you also need to spend energy to burn food, right? Eventually you will get a lot of energy, but to burn that initial food, that is energy. You need some energy to do that, okay? The exothermic process also has a similar thing, but in here, this is the product, this is the reactant, and this is the activation energy, in which the final energy of the product is more, right? So this could be a profile for anabolism. This could be the profile for catabolism, right? So this is exothermic, this is endothermic, correct? These two things together is called metabolism. So you do both of these things in your body, right? You must have heard about this, like faster metabolic rate. And so what they are actually saying is you are eating and you're burning at a very fast rate. So that's why you say a faster metabolic rate and things like that. But if you see in the energy, if you follow YouTube channels or some podcasters, they use this term catabolic window or catabolism very negatively. But it's not that. I mean, have you heard about these terms? Like, you're in the catabolic state. I said, yeah, but sometimes people do, but they are using it in a very, without understanding the process. You need catabolism to extract that. It's not bad to be in a catabolic state. You cannot always be in that anabolic state in which you're taking that and building your muscles. I mean, it's not possible. Because if you don't burn, so you are an unstoppable increasing body of mass. That is not possible, right? So you cannot